I want you to picture something with me. Not as a fantasy, but as a place that might actually exist right now. Somewhere in the quiet dark beyond everything you've ever seen. A world where the sky looks familiar but not quite right. A shade deeper, maybe heavier, where the clouds move slower because gravity pulls twice as hard as it does on your body at this very moment. Where standing up feels like wearing an invisible backpack you can never take off. And the oceans, if they exist, are so deep that sunlight never reaches their floor. Not because the water is cloudy, but because the planet itself is simply larger, broader, heavier, more patient than Earth ever was. You walk along a shoreline, and the horizon curves differently, subtly, enough that you sense something is off, even if you cannot explain it, and the air might be breathable, or almost breathable, carrying the same promise that made our own world feel alive for billions of years. And suddenly this stops being science fiction and becomes a real question. Because somewhere out there, astronomers have already seen a world that looks like this in their data, not clearly, not in photographs, but in tiny dips of starlight that whisper that something Earth-sized, or larger, is passing in front of a distant sun. This is where the idea of Earth 2, zero, comes from. And I want you to notice something subtle here. Because when people hear that phrase, they imagine a backup plan, a spare house, a second chance waiting quietly for us. But the reality is stranger than that, because we don't actually know what we're looking at. We only know that the conditions might allow liquid water, and that single detail is enough to ignite our imagination far beyond what the data actually says. Because water is not just water to us. It is oceans, storms, coastlines, biology, evolution, memory, and everything we associate with being alive. So when scientists find a planet in the so-called habitable zone, our minds rush forward and begin painting continents, forests, and skies, long before we even know whether the surface is rock, ocean, or something entirely hostile. I remember the first time I really thought about this, not as a headline, but as a physical place. And what struck me wasn't the excitement. It was how quickly the brain tries to make it familiar. Because you don't imagine alien geometry or impossible physics. You imagine standing there. You imagine looking up. You imagine whether you could breathe. And in that moment, the planet stops being an object and becomes a destination. And that is the dangerous step. Because once a place becomes a destination, the next question appears automatically, almost involuntarily. How long would it take to get there? Not in theory, not with imaginary engines, but with something we could actually build, something made of metal, fuel, and human decisions. There is something deeply human about that jump, because we do this all the time. We see a mountain and we think about climbing it. We see an island and we think about sailing to it. We see a point of light and suddenly we are packing bags in our heads. And what fascinates me is how little distance means to our intuition. You hear a number, 600, and it doesn't sound frightening. You've driven 600 kilometers before. You've flown farther than that. But space plays a different game entirely. And the moment you attach the words light years to that number, the scale begins to stretch in a way that no everyday experience prepares you for. Yet even then the mind resists, because imagination is stubborn and optimistic. It keeps telling you that if the world exists, if it might have oceans and clouds and gravity strong enough to pin your feet to its surface, then surely it must be reachable. Surely distance is just another engineering problem waiting for clever people and better engines. And that is exactly where this story really begins. Not with the planet itself, but with the simple, unsettling thought that somewhere out there, a possible second Earth is quietly orbiting its star. And the only thing separating you from standing under that unfamiliar sky is the emptiest stretch of space you have ever tried to comprehend. Before you decide whether a journey like this is worth even imagining, you have to understand why this particular world refuses to leave astronomers alone. Because the universe is not short on planets. We've already cataloged thousands of them. Giant gas worlds hugging their stars, frozen rocks drifting in darkness, bizarre systems where planets orbit in days instead of years. Yet every once in a while, something appears in the data that feels uncomfortably familiar. Not identical, not safe, but close enough that you instinctively lean forward as if the numbers themselves are trying to tell you something. Kepler, 22b, is one of those worlds. And what makes it compelling isn't that we know what it looks like. It's precisely that we don't, because the few facts we do have sit right on the boundary between hope and uncertainty, and that is where imagination becomes impossible to ignore. The planet orbits a star that belongs to the same general family as our Sun, a G-type yellow dwarf, slightly smaller, slightly cooler, but close enough that the light falling on that world would not be alien in the way red dwarf systems feel alien. It would not be a dim crimson twilight or a violent flare-ridden sky. It would be something more stable, more familiar, a steady stream of energy capable, at least in principle, of warming a surface for billions of years. That alone changes the tone of the conversation, because stable stars buy time, and time is the quiet ingredient behind everything biological. Oceans need time to settle. Chemistry needs time to become messy. Evolution needs time to make mistakes and keep the ones that work. And Kepler 22b appears to have had that time. Then there is its orbit, sitting inside what scientists like to call the habitable zone, a phrase that sounds more confident than it really is, because it does not guarantee life or oceans or even a solid surface. It simply marks the region where temperatures could allow liquid water if the atmosphere cooperates. If the chemistry aligns, if a dozen variables behave themselves, yet even that conditional possibility carries enormous weight, because liquid water is not just another substance. It is a solvent that encourages complexity, a medium where molecules meet, collide, assemble, and occasionally stumble into something that begins to copy itself. When you place a planet in that zone around a stable star, you're not saying life exists. You're saying the door is open, and that is enough to change how we think about it. But then the numbers tilt again, because Kepler 22b is larger than Earth, about 4 times our planet's radius, and this is where the mystery deepens. Instead of resolving, since size alone does not tell you composition. A world that large could be a massive rocky planet with enormous continents and thick atmospheres, a place where mountains dwarf Everest and oceans spread wider than anything we've known. Or it could be an ocean world entirely. A global sea, hundreds of kilometers deep with no land at all, where the surface is water from horizon to horizon, and whatever life exists evolves in darkness far below. There is also a less comfortable possibility, one that reminds you how little we truly know. That Kepler 22b might resemble a mini Neptune, a dense atmosphere of hydrogen and volatile gases wrapped around a core, crushing pressures, building downward until the concept of standing on a surface stops making sense. A world that looks promising from afar, but becomes lethal the moment you approach. What fascinates me is how all 3 possibilities coexist in the same data, because we are not choosing between them. We are suspended between them. And that uncertainty forces you to confront how thin our knowledge really is. We have a hint of size, a hint of orbit, a hint of stellar type. And from those fragments, we construct entire landscapes in our minds, coastlines, storms, alien seas, or suffocating atmospheres, and each version changes what the journey means. If it is rocky, you imagine walking there. If it is ocean, you imagine diving there. If it is gaseous, you realize the destination might not even allow you to land. The planet becomes less a place and more a question. And the more you think about it, and the stranger it feels. That something so uncertain can still pull so strongly on our curiosity, as if the possibility of a temperate world orbiting a quiet star is enough by itself to turn a distant dot into somewhere you can't stop thinking about. Now comes the part where the imagination begins to resist, because up to this point you can still pretend this is just another distant destination, another island across a larger ocean. But the moment we talk about the distance to Kepler, 22b, the story shifts from curiosity to scale. And scale is where human intuition quietly breaks down. The planet sits roughly 600 light years away. Sometimes you'll see the estimate drift slightly higher, sometimes a little lower. But it doesn't matter, because once you attach the phrase light years to any number, you are no longer dealing with something your everyday experience can guide you through. A light year is not a measure of time, even though it sounds like one. It is distance, the distance light travels in 1 year. And light moves at about 300,000 kilometers every second, which is already a speed so absurd that your brain tries to round it down into something manageable. But it isn't manageable, because at that speed light could circle the Earth more than 7 times in a single second. And even that comparison feels too small, like trying to explain an ocean using a glass of water. Let me slow it down in a way that feels almost physical. Light leaving Earth reaches the moon in about 3 seconds, barely enough time for you to blink. It takes 8 minutes to reach the sun, meaning the sunlight warming your face right now began its journey while you were still making coffee. To cross the orbit of Pluto, light needs about 5.5 hours. And that already feels enormous, because our entire solar system stretches farther than most people ever imagined. Yet all of that, every planet, every asteroid, every icy object at the edge, still fits inside a region that light crosses in a single afternoon. Then you step beyond that, beyond the heliosphere, beyond the drifting boundary of the sun's influence. And you keep going for a year at the speed of light, not a day, not a week, but an entire year moving at the fastest speed nature allows, and you have traveled 1 light year. And Kepler, 22b, is 600 of those stacked one after another, like an empty corridor stretching so far that the far end dissolves into abstraction. What unsettles me most is not the number itself, but the time embedded inside the light we receive. The photons captured by our telescopes left that system roughly 6 centuries ago, which means when that light began traveling toward us, human history looked very different. Kingdoms rose and fell. Continents were mapped. Languages evolved. And all the while, those photons kept moving silently through interstellar space, uninterrupted, indifferent, carrying a faint signature that only now reaches us. When explorers crossed oceans on wooden ships, that light was still in transit. When entire civilizations transformed, it had not yet arrived. You begin to realize that observing Kepler 22b is less like looking far away and more like looking backward, as if distance and time have folded together into a single experience. If you try to translate the distance into kilometers, the number becomes almost theatrical. Roughly 5 quadrillion and 600 trillion kilometers. A figure so large that the zeros stop conveying meaning and instead become decorative, And this is where I always notice something interesting about the mind. Because when numbers grow too large, you don't feel them anymore. You simply label them far and move on. Yet the physics doesn't simplify itself just because we've given up imagining it. Space does not compress to match our intuition. It remains vast, patient, and mostly empty. And that emptiness is the real barrier, not mountains, not storms, not gravity wells, but nothing, an enormous quiet. Nothing that stretches between stars and quietly refuses to be crossed quickly. Once you accept the distance, the next instinct is almost automatic. You start looking for the fastest thing we have and you point it toward that distant star, because that's how we solve problems on Earth. We build faster vehicles, we shorten travel time, we compress geography with engineering. And for a moment it feels like the same logic should apply here. But space has a way of exposing how small our technological achievements really are. If you ask me what the fastest object humanity has ever built is, I might answer with something dramatic: a rocket, a deep space probe, maybe some classified experimental craft. But the actual answer is less glamorous and more revealing. It's a spacecraft falling toward the sun. The Parker Solar Probe reaches peak speeds, approaching 700,000 kilometers per hour when it dives close to our star. And that sounds absurdly fast. Fast enough to circle Earth multiple times in a single hour. Fast enough to cross continents in minutes. Yet even that speed is misleading, because the probe achieves it by borrowing gravity, by falling deeper into the sun's well, not by cruising steadily through interstellar space. So instead of using that extreme case, it makes more sense to look at something already leaving the solar system, something genuinely escaping into the dark. And the obvious candidate is Voyager 1, a machine launched in the 1970s that is now farther from Earth than anything else we've ever built, quietly drifting outward at roughly 61,000 kilometers per hour. That speed once felt extraordinary, and in human terms it still is. If you could ride something that fast, you would cross entire countries before finishing a conversation. Yet the moment you compare it to the scale between stars, the number begins to shrink. Not physically, but psychologically, like watching a jet plane from space. Still fast, but no longer impressive against the curvature of the Earth. If you take Voyager's speed and aim it directly at Kepler, 22b, and this is the part where the arithmetic becomes uncomfortable, the trip would take on the order of 10 to 11 million years. That number isn't dramatic in the usual sense. It's almost too large to feel shocking. But if you translate it into something biological, it becomes unsettling. 10 million years ago, our species didn't exist. Our ancestors were early primates. Forests covered regions that are now deserts. Entire evolutionary branches had yet to appear. And if a spacecraft had been launched back then, using the best technology available today, it would only now be approaching its destination. The journey would outlast languages, nation, religion, and probably the continuity of civilization itself. And the ship, if it even survived that long, would be a relic traveling through a universe that had already forgotten who sent it. There is also a quieter problem that doesn't show up in the simple math, because spacecraft are not eternal. They erode. They accumulate microscopic damage. They are bombarded by dust grains, moving at enormous relative speeds. They endure radiation, temperature swings, mechanical fatigue, and we already see this happening with probes that have traveled only decades. Instruments fail, power systems degrade, communication weakens. And that's over spans of time that are tiny compared to millions of years. A vehicle attempting a journey of that length would not just need fuel and direction, it would need to survive a duration longer than most complex life has existed on Earth. And suddenly the issue is no longer propulsion alone. It's durability on a scale we have never engineered for. Not even close. This is the moment where the conclusion stops being speculative and becomes blunt. With chemical rockets and conventional propulsion, the trip is not merely difficult, it is effectively impossible. Not because we lack courage or imagination, but because the numbers quietly refuse to cooperate, and the uncomfortable realization is that even our fastest machines are not really fast in cosmic terms. They are just quick inside a very small neighborhood. Impressive within the solar system, but almost motionless when measured against the space between stars. When speed fails, the next idea feels almost philosophical rather than technological. Because instead of trying to outrun the distance, you begin to accept it. You stop asking how to get there quickly and start asking whether time itself can be absorbed into the journey. And that is where the concept of a generation ship appears. Not as a clever trick, but as a quiet surrender to physics. The idea is simple in a way that makes it unsettling. If one lifetime isn't enough, then you don't send one lifetime, you send many. You build a self-contained world. Not just a spacecraft, but an ecosystem. A floating city sealed inside metal and radiation, shielding, carrying soil, water, air, microbes, and a small population of humans who will never see the destination because they are not the travelers in the usual sense. They are the beginning of a chain. Imagine improving our propulsion dramatically, not to anything exotic, just to 1 or 2% of the speed of light, which already sounds impossibly ambitious by today's standards. Yet even at those speeds, the journey to Kepler 22b stretches to 30,000, maybe 60,000 years. A span so long that the launch itself becomes a historical event, remembered only in archived recordings. You would board knowing that you are not going somewhere. You are becoming part of a process. And your children would grow up inside rotating habitats that simulate gravity, looking at artificial skies, projected on curved ceilings, learning about oceans they will never see, studying maps of a planet that still lies tens of thousands of years ahead. Their grandchildren would inherit the same corridors, the same machinery humming behind walls, the same recycled air that has passed through countless lungs before theirs. Technically, the challenge is already intimidating because nothing can be wasted. Every drop of water must be purified and reused. Every molecule of oxygen carefully regenerated. Agriculture must function in closed loops. Ecosystems must be stable over millennia, and any imbalance could cascade slowly into disaster. Yet the deeper difficulty is not mechanical. It is human. Cultures change, even over centuries. Priorities shift. Myths replace facts. And inside a generation ship, the original mission risks becoming abstract, something mentioned in educational modules. Rather than felt as urgency, I try to imagine being born in the year 20,000 of such a journey, walking through corridors where every surface is engineered, where the stars outside are distant pinpoints behind shielding, and someone tells you that your ancestors left a planet you've never seen, heading toward another you won't reach, and you realize your entire life unfolds in transit, not between two places you recognize, but inside a purpose handed down like a tradition. There is also the fragile psychology of confinement, because even if the habitat is large, even if landscapes are simulated, everyone knows the boundary is real. Beyond the hull there is vacuum. And the idea of turning back might arise not as rebellion, but as fatigue. a slow erosion of motivation over generations. Maintaining continuity would require governance systems that survive thousands of years, educational structures that keep the mission meaningful, and social stability that prevents conflicts from threatening life support, since in such a closed environment, a single serious failure is not localized. It touches everyone. The ship becomes less like a vehicle and more like a civilization in miniature, isolated, self-referential, evolving in ways its designers cannot fully predict. What fascinates me is that in this scenario, Earth gradually transforms into a story, not a place, something described in archives and reconstructed in simulations, while Kepler 22b becomes almost mythological, a promised horizon that defines identity without ever being experienced directly by those who carry the mission forward. People would be born, live entire lives, and die in the quiet space between stars, guardians of a trajectory they did not choose but inherited, and the journey stops feeling like exploration and starts feeling like a long continuity of human existence detached from any natural world, suspended in engineered equilibrium, moving slowly through a darkness that no generation will ever see end. At some point, the mind starts to rebel against all this patience, against the idea of drifting for tens of thousands of years or sending civilizations instead of travelers, and you begin to wonder whether the mistake is not in the engines but in the question itself, because we keep asking how fast we can move through space. When physics quietly suggests another possibility, what if you don't move through space at all? What if you move space instead? This is the strange loophole hidden inside Einstein's equations. The realization that relativity limits how fast objects can travel locally. Nothing can outrun light within space-time. But the theory says nothing about space-time itself stretching, compressing, or flowing. And we already see this happening on cosmic scales where galaxies recede faster than light, not because they are breaking the rules, but because the space between them is expanding. If you try to picture this, it helps to abandon rockets entirely and imagine standing on one of those moving walkways at an airport. You are walking at a normal pace, nothing extraordinary, yet the floor beneath you carries you forward faster than your legs alone could manage. And from your perspective, you never exceeded your own speed limit. You simply let the environment do the work. A warp drive applies the same logic to space-time, compressing the region in front of a spacecraft and expanding the region behind it, creating a kind of bubble where the ship itself remains locally stationary, not accelerating in the usual sense, not feeling crushing forces, just floating inside a pocket while the universe around it rearranges. The destination comes closer, not because the ship rushes toward it, but because the distance itself shrinks. And once you think about travel that way, the impossible journey to Kepler 22b begins to look less like a race and more like geometry. In principle, if you could engineer such a distortion moving effectively 10 times faster than light, the trip that once required millions of years collapses to about 60 years, long enough for a single lifetime, a departure in youth and an arrival in old age. And if the distortion reached 100 times the speed of light, the journey drops to roughly 6 years, suddenly comparable to long-duration missions we already imagine within the solar system. What's unsettling is how ordinary these times begin to feel. Because once the distance contracts, the planet stops being mythological and starts looking like a remote expedition. Still dangerous, still unprecedented, but no longer beyond comprehension. The abyss does not disappear. It simply folds, but this is where the elegance of the idea collides with the stubbornness of reality. because the mathematics that allows such a bubble demands something we have never observed in usable quantities. Negative energy or exotic matter with properties that defy our everyday understanding of mass and gravity. The equations do not forbid it, which is why the concept remains intriguing. Yet they require distributions of energy that, in early estimates, rivaled the mass energy of the entire observable universe. A requirement so absurd it turned the warp drive into a thought experiment rather than an engineering plan. Later refinements softened the demand, reducing it to something like the mass of Jupiter, perhaps even less under carefully shaped geometries, but even that is still far beyond anything we can manipulate. And it leaves us in a peculiar position where the theory whispers that faster than light travel might not violate relativity, while the practical side quietly reminds us that having permission from equations is not the same as having the tools to act on it. I find this tension strangely compelling because it reveals how physics sometimes opens doors that technology cannot yet walk through, and the warp drive becomes less a blueprint and more a horizon, a reminder that the structure of space-time might allow shortcuts our current civilization cannot build, leaving Kepler 22b suspended between impossibility and imagination, not unreachable in principle, but waiting for a level of understanding and control over energy and geometry that we have only just begun to glimpse. When you put all of this together, the distance, the physics, the fragile ideas we invent to bridge the void, Kepler 22b stops being just another exoplanet and becomes something more reflective, almost like a mirror held up to our species. With the technology we possess today, the journey stretches beyond meaning. Millions of years of drift through interstellar darkness, a duration longer than human civilization has existed, longer than most species survive. A trip so slow that the concept of departure and arrival dissolves into geology, with propulsion that might emerge in a distant future, perhaps pushing a fraction of light speed. The voyage compresses into tens of thousands of years, still impossibly long for individuals, yet short enough for a chain of generations. A civilization launched like a seed, growing in artificial sunlight while the stars shift imperceptibly outside its hull. With the speculative geometry of warped space-time, the same distance contracts into a single lifetime, an expedition rather than an inheritance, but one balanced on physics we barely understand and energies we cannot yet command. Three versions of the same journey, each revealing something different, not about the planet, but about us. I keep returning to the quiet fact that Kepler 22b is there, regardless of what we decide, orbiting its star every few hundred days, bathed in steady light, possibly covered by oceans that have never known wind from our sun, possibly wrapped in clouds that formed before humans learned to write, a world continuing its cycles without any awareness that somewhere far away we are measuring its shadow. There is something humbling in that indifference, because it reminds you that the universe does not wait for our readiness. It simply offers possibilities and leaves us to decide how much we are willing to invest in reaching them. We often speak about exploration as if it were inevitable, as if curiosity alone guarantees expansion. Yet every real journey carries cost, not only energy and engineering, but commitment, risk, and the willingness to step away from the familiar without any promise of return. I sometimes imagine the moment of decision, not the launch itself, but the quieter conversation beforehand, someone explaining that the mission is one way, that communication delays stretch years, then decades, then centuries, that the sky you leave behind will not be the sky you see again. And you realize exploration at this scale is not just about discovering new worlds, it is about redefining home. The word starts to lose its geographic meaning and becomes something portable, carried in memory, in culture, in whatever fragments of earth we choose to bring along. The idea is both unsettling and strangely liberating because it suggests that what makes a place human is not its gravity or atmosphere, but the decision to inhabit it. Kepler, 2b, therefore becomes less a destination and more a question posed across 600 light years, asking whether we are a species that observes from a distance or one that eventually crosses it, whether the vastness between stars discourages us or quietly invites us to grow into it. The answer is not written in equations alone, because equations only describe what is allowed, not what is attempted. Somewhere between caution and audacity, between patience and impatience, lies the choice to move outward. Not because the journey is easy, but because the existence of another possible sky makes staying still feel incomplete.